This is the practice exam B for Unit 3, Math 1050. So we need to graph these exponential functions. Remember, exponential functions have a horizontal asymptote, usually along the x-axis at y equals 0, unless there's a vertical translation. Like with that, +1 moves the entire graph up 1 unit, including the horizontal asymptote. So the horizontal asymptote is right there at y equals 1. Now we just need to plot a few additional points, one of them being the y-intercept. So I'm going to let x equals 0. 0 subtract 1 is -1. 2 to the -1 power is 1/2. 1/2 plus 1 is 1.5. Let x equal 1. 1 subtract 1 is 0. 2 to the 0 power is 1. 1 plus 1 is 2. Then 2 subtract 1 is 1. 2 to the first power is 2. 2 plus 1 is 3. There's the graph. The domain, or the set of possible input values, you can see it goes all the way to -infinity, and it's going to continue to go to the right, so x can go to +infinity. So the possible inputs, -infinity to +infinity, that's the same for any exponential function. Range, this y value, the y values of this graph are going to go no lower than y equals 1, so the range is from 1 to infinity, not including 1. For part B, we have a vertical translation down 2 units. So now the horizontal asymptote will be right here at y equals -2. So when x is equal to 0 for the y-intercept, we have 0 plus 1. It's 1. 1/2 to the first power is 1. Or 1/2 to the first power is 1/2. 1/2 subtract 2 is -1.5. When x is equal to 1, we have 1 plus 1 is 2. 1/2 to the second power is 1/4. So I'm actually going to go in the opposite direction then. Let's do -1. Let's see, that will work better. -1 plus 1 is 0. 1/2 to the 0 power is 1. 1 subtract 2 is -1. So -1 comma -1. And then I'm going to go -2. -2 plus 1 is -1. 1/2 to the -1 power is 2. 2 subtract 2 is 0. So the graph looks like that. It's exponential decay because the base is between 0 and 1. So, like in the previous example, the domain is all real numbers. The range will go no lower than -2 on the y-axis, so -2 up to +infinity, not including -2. Question 2, e right now can't cancel the natural log because we have this coefficient in front of the natural log. But using the power rule, we can move this 2 up in front as an exponent, or up from the front to an exponent of the 4. So this becomes e to the natural log of 4 squared. Now e cancels natural log. 4 squared is equal to 16. On part B, we can condense these into one logarithm, log base 6, and this is an example of the quotient rule because there is a subtraction sign between those two logarithms. So 72 divided by 2 is 36, so log base 6 of 36, we can change 36 into 6 squared. So the log base 6 cancels the base 6, and the answer is 2. For part C, we want to get matching bases. 1/9 is the same as 3 to the power of -2. So log base 3 cancels base 3, and we get -2. Logarithmic functions, if you recall, have a vertical asymptote, normally here at x equals 0, unless there's a horizontal translation. In this case, we're going to the left 1 unit. So the vertical asymptote is at x equals -1. Vertical asymptote, remember, is a domain restriction. So the domain of this is going to be to the right of -1, so from -1 to infinity. So we need to plot a few additional points. If x is equal to 0, 0 plus 1 is 1. And remember, whenever 1 is inside of a logarithm, log base 2 of 1 is equal to 0. Now this is a base 2 logarithm, so I want whatever is inside of here to come out to be a power of 2, like 2 or 4 or 8. So if I plug a 1 in for x, 1 plus 1 is 2. So I'm going to use 1 for x. 1 plus 1 is 2. Log base 2 of 2 is equal to 1. And then the next power of 2 would be 4. So if I let x equal 3, 3 plus 1 is 4. Log base 2 of 4 is equal to 2. The domain, as you can see, the possible x values begin at -1, not including -1, but starting at -1 and to the right. So -1 to infinity, not including -1. The range is all real numbers. Question 4, we're expanding. We have the product of these two terms here. So to expand, we're going to use the product rule. Log base b of the square root of x plus log base b of y squared. Remember, logarithms and radicals don't do well together, so I'm going to change the square root of x into x to the 1/2. And then last is the power rule to move the exponents in front of the logarithm. So we're going to have 1/2 log base b of x plus 2 log base b of y. For part B, this is a quotient inside here. So we're going to use the quotient rule, which says we can separate that using subtraction. So it's going to be log base b of the numerator minus log base b of the denominator. Now this has a product, so we need to separate this logarithmic expression into 2 more logarithms to separate that product, to expand that product. So this one's going to expand into log base b of x plus log base b of y squared, and then we still subtract this log base b of z cubed. Now final step is to use the power rule to move these exponents in front. So log base b of x plus 2 log base b of y minus 3 log base b of z. For question number 5, now we're going in the opposite direction. We're going to condense into a single logarithm. So I notice this one has an exponent, or a coefficient that needs to be moved back up as an exponent. So log base b of x to the 1/2. Now when we condense, because this is a minus sign, we're going to use the quotient rule. Quotient means fraction, so log base b, now we're going to form a quotient. X to the 1/2 is in the numerator, and y is in the denominator. For part B, I'm going to start by moving the coefficients back up as exponents. So this is natural log of x squared plus natural log of y cubed plus natural log of z. Now I'm just going to combine those into one natural log using the product rule. And then we combine these two, again, using the product rule, because there's a plus sign, into one natural log. So the x squared y is just going to multiply the z to form the product x squared times y times z. All right, question 6. We're solving exponential equations. So what we need to do here is get the exponential term right here all by itself so that we can cancel the base. But we can't cancel the base until we get rid of the coefficient and this minus 1. So add 1. Now divide by 2. Now we can cancel the base on that exponential term using a log base 4. So now x plus 1 is equal to log base 4 of 8. And then we can subtract 1. So that's the exact form. The approximate solution will be found by doing a change of base formula using a calculator. So that's log 8 divided by log 4 minus 1, and that's approximately equal, actually, it's exactly equal to 0.5. For part B, similar situation, we got to get e to the x plus 2, we got to get this term isolated so that we can use natural log to cancel the base e. So we got to get rid of the coefficient of 3 and that plus 4. So we're going to minus 4. Now divide by 3. Now cancel base e using natural log. Natural log cancels base e. And then subtract 2. So x is equal to the natural log of 3 minus 2, and then the approximate form is approximately negative 0.9. All right, question 7, we're solving logarithmic equations now. Similar way of doing it, we have to isolate the logarithmic term and then use a base to solve. And there's a typo here. I apologize. That should be a log base 3, not a log base x. That's a log base 3. So in order to use a base on both sides, we have to isolate the logarithmic term. So we have this plus 3 that we need to get rid of. So we're going to subtract 3. Now we cancel the logarithm using, in this case, a base 3 because it's a base 2 logarithm. So 3 raised to the log base 3 are inverse operations, so those are going to cancel each other out. So we have x minus 1 is equal to 3 squared, which is x minus 1 is equal to 9, or x is equal to 10. For part B, recall from our discussions in class, you cannot solve a logarithmic equation if you have two logarithms on the same side of the equation. So we have two logarithms here on the left side. We cannot solve it until we condense into a single logarithm And we're going to use the product property because we have a plus sign between the two logarithms. The 2x and the x minus 5 are going to form a product. So now we have one logarithm on the left side that we can now cancel using the base 10, because that's a base 10 logarithm. So log and the base 10 cancel each other out. And then I'm going to distribute the 2x into that parenthesis. So it's going to become 2x squared minus 10x equals 10 squared, which is 100. And I'm going to subtract that 100 to the left, so it's going to be 2x squared minus 10x subtract 100 is equal to 0. So we have a quadratic equation now that we can hopefully solve by factoring. I'm going to go ahead and factor out that 2. And then that itself will factor into x minus 10 and x plus 5. The 2 here in front at this point is irrelevant. It's not going to affect the solution to this equation. We're still going to have x equals 10 and x equals negative 5. So x equals 10 or x equals negative 5. Now recall, when solving logarithmic equations, we need to check. Matter of fact, we should have checked in the last one if it's extraneous. Here, 10 minus 1 is 9. 9 is positive. Inside of a logarithm, you can have positive numbers. Every number that's inside of a logarithm needs to be greater than 0. So 10 is good. Over here, if you plug in 10, 10 times 2 is 20, 10 minus 5 is 5, so that's good. Negative 5, 2 times negative 5 is negative 10. Negative 10 is not in the domain of logarithm, so x does not equal negative 5. It's extraneous, so the solution is, again, x equals 10. Okay, for question 8, these are applications of exponential functions from section 4.5. We want our $8,000 investment to double. Now the key word here is it compounds continuously. So continuously compounding interest, if you recall, is the amount in any given time is equal to the principal investment times base E raised to an exponent of rate times time. So the principal investment is our $8,000. The rate is what we're trying to find. Time is how long will it take? Let's see, 25 years. So we need to solve this equation for R. What does the rate need to be? Now we need to have, in order to solve for one particular variable R, we have to have values for all of the other variables, principal value, the amount of time, but we also have to have a future amount, and it says it in here. Suppose you invest, how long will it take for your money to double? So there's the future amount. 16,000 is equal to our principal investment times E to an unknown rate in 25 years. So we divide by 8,000 on both sides, we're going to get 2. Now we need to cancel the base E so that we can solve for the variable. Remember, we can't solve for a variable if it's an exponent, so cancel the base. In this case, we use natural log to cancel base E. So the natural log of 2 is equal to R times 25. So we divide both sides by 25. So the rate is equal to natural log of 2 divided by 25, which is approximately equal to 0.0277. So the interest rate is 2.77%. Question 9. We have a 10-gram sample of a radioactive isotope, and it mentions a half-life, so this is going to act according to the exponential growth or exponential decay function that we talked about in section 4.5, which is the amount at any time t is equal to the initial amount times base e raised to the kt. It's essentially the same formula as continuously compounding interest that we used in question 8. So k is the relative, in this case, the relative decay rate, because we have a 10-gram sample that's going to decay, get cut in half every 432.2 years. So what we don't know is the relative decay rate. So we need to solve this equation for k, which means we need to plug in values for the initial, for the future amount, and the amount of time. So we have an initial sample here of 10 grams. We don't know the relative decay rate, but we know that if we allow time to be 432.2 years, then half of the sample will remain. That's the half-life. So we can plug in values for all of the other variables so that we can solve for k. And remember, if it's a decay rate, k should be negative. So divide both sides by 10, we get 5 divided by 10, or 1/2, equals e to the k times 432.2. Now we use a natural log on both sides. So if we do natural log here and natural log there, natural log is going to cancel base e. So natural log of 1/2 equals k times 432.2. So k is equal to the natural log of 1/2 divided by 432.2, which is about negative 0.001603. So that's the relative growth rate. So now the other part of the question is we got to use this model to find the remaining amount remaining after 175 years. So the model now is the amount at any given time is equal to our 10-gram sample, base E. Now the relative decay rate is negative 0.001603 t. So that's our model. Now we need to find out how much remains of the 10-gram sample if we let t equal 175 years. So then the amount after 175 years is simply using the formula now, plugging in t equals 175. And from that, we get about 7.55 grams. And we should always pause when we're doing an application problem. When we have an answer, we got to make sure that it fits the situation. A full half-life is 432 years. So if we're only doing 175 years, less than half should have decayed. So starting with the 10 gram, it's only decayed to 7.55 grams because not a full half-life has happened yet. So this seems to make sense. Okay. Question 10, we have now a compound interest that's compounding monthly. So we're going to use this formula here where the principal investment, that should actually be a P for principal investment. Principal investment is $15,000. The interest rate is 6%, which is 0.06. The number of compounding cycles per year is 12 because it compounds monthly. And then the time is 20 years. So we simply just need to plug all this into the formula. The amount after 20 years is equal to the principal investment. And then the rate is, remember, 0.06. And then n times t is going to be 12 times 20. So this is just a matter of plugging this into your calculator. And from that, we're getting 49,000 $653.07.